So start chapter 8 today, and chapter 8 is on gases. So gases and their behavior. Chapter 10 is actually going to be on liquids and solids. So part of the reason that gases had their own chapter separate from that of liquids and solids is that liquids and solids, we do have intermolecular forces between the atoms or between the molecules, right? If I was to have water in its liquid form, right, I have covalent bonds between the oxygen and the hydrogens, but then between one oxygen molecule and another oxygen molecule, I have connections. So intermolecular forces, or connections between those particles. I have those in solids, I also have them in liquids, but when I get to a gas, I don't have any of those connections. We actually break those. So they get their own chapter because they're unique in the fact that I don't have any connections between the particles. Because of that, each particle acts independently of its neighboring particle. With liquids and solids, its behavior is basically mostly based on what those connections are, and the particles do interact with each other. But these guys, we have actually no connections. Between particles in a gas. So the individual gas particles act independently of each other. Right back at the beginning of the semester, we were talking about the differences between solids, liquids, and gases, right? I would have drawn a picture on the board where I said these were our particles, and then in a solid, I would have connected them, right? Lots of connections, right? Which is why it has a definite shape and a definite volume, right? If I was to put it into a different container, because of all of those connections, the shape stays the same, its volume stays the same, that sort of thing. And then when we had a liquid, right, I broke some of those connections. We still had some, but not all of them were connected anymore. So because this one here isn't connected, we could actually move it out, right? I can't change the volume. Remember, volume is the amount of space that it occupies, and it's still connected. But because I moved it out like that, my shape is different, right? This one's still connected, so I can't like move it to the corner of my iPad, but I can do this with it, right? So my liquid, the volume doesn't change, right? The amount of space that it takes up because those particles are still connected, but my shape can change because I have some freedom for the individual particles to move a little bit. When I get to a gas, see if I can erase, yeah, it all erases. But in a gas, these dots aren't connected to each other at all. So if I want to take this dot and move it over here, I can, right? And now it takes up a different amount of space. So the individual particles act completely independent of each other. The properties of a gas actually depend only on 4 things. So the first one is going to be the volume. And let's just write volume. So volume, and these are in no particular order, they're just in order that I think of them. So volume, we'll use V as our abbreviation. And then we did just define this, but we want to remember this is the amount of space that a substance occupies. Right? It's not how much I have, right? The amount that I have, that's our SI unit for that was the number of moles. It's not how much matter it's made up of, that's my mass, right? This is how much space it takes up. I could have a little bit of stuff that takes up a lot of space, right? It would have a small density, my mass to volume ratio. So be careful, don't get volume mixed up with how much I have. I could have something that takes up a lot of space and have very little bit of it. So volume, just how much room does it occupy? The amount of space that an object occupies, right? Not necessarily indicative of how much I have. That's a different unit. So volume. The other one is pressure, and we haven't talked very much about pressure, this semester. But these particles are moving around. Remember, unless we're at absolute zero, they're moving. So if I was to take particles and put them in a container, so let's put a lid on it just for kicks, and these guys are acting independently, right? It's not like if one moves left, they all move left. So it is possible that this particle moves this way and this particle moves this way, and they bang into each other. They can collide. The particles can collide into the walls of the container, right? Because they're all moving. Let's say this one goes this way. So we're going to define pressure in this chapter as the forcefulness of those collisions. So if you have a lot of collisions, we're going to have a high pressure. If you have a little bit of pressure, then you have less collisions. So this is going to be the forcefulness of particle collisions. Usually it's defined as with the walls of the container, but it could be with each other too. So I'm just going to say the forcefulness of particle collisions. The more collisions you have, the higher the pressure. The less collisions, the lower the pressure. We'll use the amount as to correlate to forcefulness. So more collisions equals higher pressure. And then less collisions. Again, it's really forcefulness, but if you have less of them, the sum is less, this part of the force. So less collisions, lower pressure. Temperature is also going to be a factor. And remember, temperature was the average kinetic energy of our substance. Remember, kinetic energy is energy in motion. We can actually think of this as a measure of particle motion. So if we have a higher temperature, we have more motion. Particles are moving faster. We can think about it that way, right? They're moving with more kinetic energy is how we would actually say it. But if you want to think about them as just moving faster. Lower temperature, right? Moving slower. My average kinetic energy is less. They're moving with less energy. So moving slower. So we can think of it as a measure of particle motion. Remember, at absolute zero, right, the absence of temperature, we have no average kinetic energy. My particles are not moving. So absolute zero, motion ceases. Right, absolute zero. That was 0 Kelvin, right? No particle motion. If it's 0 Kelvin, I have 0 kinetic energy, because remember, that's what I'm measuring when I measure temperature. So no energy associated with motion, because there's no motion. And then our fourth one is the amount. Again, don't get amount mixed up with volume. Volume is how much space it takes up. Amount is how much I have. And you can have a very small amount of stuff that takes up a lot of space, or you could have a lot of stuff that takes up a small amount of space. So amount, and that's actually, we're going to use N. It's going to be my number of moles. It's the number of moles of the gas. And that's it. Notice how the identity of the gas isn't here. I'm not actually writing like molar mass or chemical formula. All I really care about is how much space does it take up? What is the forcefulness of their collisions? How fast are they moving, right? How much energy are they moving with? And then how much do I have? The relationship between these four factors, the amount, the temperature, the pressure, and the volume, are our gas laws. So the first section of this chapter is actually just going through some of our gas laws. So gas laws are the relationships between volume, pressure, temperature, and the number of moles. Before we talk about specific gas laws, I do want to go through and talk about kinetic molecular theory first. As we go through the gas laws, I actually want to relate them back to kinetic molecular theory. So kinetic molecular theory. So essentially what this is a list of 5 statements that define the behavior of gases. And some of them we've kind of already talked about as I went through just the introduction. So the first one, gases are composed of small particles in continuous motion, unless of course we're at absolute zero. So gases are composed of small particles in continuous motion. They do tend to travel in straight lines. So when I drew that picture above where I was talking about the pressure and I had those little arrows showing their movement, none of them were curved, right? They were all straight arrows. So they travel in straight lines. And they do change directions when they collide. With each other or with the walls of the container. So if I was to draw a container again, and I have this gas particle, and it bangs into the wall, it's then going to bounce back off that wall. It's going to change directions. It's not going to somehow curve and miss the wall. So they're traveling in straight lines. They change directions once they collide. And then again, unless we're at absolute zero, they're constantly moving. We're not going to ever be at absolute zero. So for us, they're in constant continuous motion. Our second statement, most of a sample of gas is probably the better way to say it, is empty space. What we mean by that is the particles are really spaced out. The actual volume of the container that they're in compared to the volume of the gas particles, the volume of the gas particles would actually be negligible compared to that container, right? If I was to draw a container again, and then these dots are representing my gas particles, and then everything between those dots and the outside of the inside of my container is empty space. If I was to figure out the volume of just the dots compared to the volume of that rectangle, the volume of those dots is negligible compared to the volume of the rectangle. So the entire thing is my sample of gas. The little dots are the actual gas particles. Most of the things in that box is empty space. So the volume of the particles is negligible compared to the total volume of the gas. Right? Basically everything between those particles is just empty space. We could say the particles have lots of space between them. They're not really close to each other. They're pretty spread out. Right? Spread out. My third one, and we've talked about this one already, gas particles act independently of each other. So independently of each other, right? There's no attractive, those were those intermolecular forces I talked about that solids and liquids have. No attractive or repulsive forces between them. And part of that has to do with the fact that they're so spread out, right? There's so much empty space between them. What we're talking about, every time I talk about a gas in this chapter, we're talking about ideal gases. There actually is a separate equation, a separate way to look at real gases versus ideal. In real gases, if you have a small volume or a high pressure, you can have some attractive forces between them, and there would be a correction in that equation for that. We're going to ignore that. So we're just saying, ideally, my gas particles are all really spread out. There's no attractive or repulsive forces between them. Thus, each particle acts completely independent from its neighboring particle. Our fourth one, the total kinetic energy of the gas particles is constant. And that's, of course, at constant temperature. Remember, temperature is a measure of kinetic energy, so if you change the temperature, you're changing this. But assuming we're not doing that, so at constant temperature, the total average kinetic energy is constant. So what that means when they collide with each other, those collisions are what are called elastic. So collisions are elastic. Elastic collisions, there's different types of collisions, but elastic collisions are collisions where there's no increase or decrease in overall energy. So energy remains the same. Net energy remains the same. So collisions are elastic. So if I have this particle and this particle, and then the first one bangs into the second one, so he bangs into that one, the energy that the first particle has is then transferred to this energy of the second particle, and then it moves with the same amount. So it's not like slowing down or speeding up when they collide. You can think about them as remaining the same. Right? If they collided and then slowed down, remember our kinetic energy, we're using that as a measure of motion, then it wouldn't be constant. So when they collide with each other, they just kind of impart the energy to the other one and then bounce off, and total energy doesn't change. And then 5, we talked about this one just when we were talking about number 4, the average kinetic energy is proportional to Kelvin temperature. If you increase the temperature, then you're increasing the energy. So the average kinetic energy is proportional to Kelvin temperature. So kinetic molecular theory, sorry, I'm getting tongue-tied on you. My 5 statements, right? Gases are small particles. They're moving constantly in straight lines. When they bang into each other, they collide. However, when they bang into each other, they're not gaining or losing energy, so energy remains constant. Unless we change the temperature, then our energy is going to change. They act independently of each other, right? There's no attractive or repulsive forces between them, and they are spread out, right? Most of the volume of my gas is empty space.